Hey, welcome everybody. So in this video, we are going to explore some of the connections between linear algebra, in particular, looking at matrix multiplication and thinking about matrices as defining mappings from, say, R2 into R2 if I'm working with 2 by 2 matrices. So we're going to explore the connections between linear algebra and how they may apply to generating and moving around computer graphics. So here we're looking at a horse, computer graphic of a horse. You can see that it has been triangulated. And over on the right, we have an image of Yoda, right, which has also been triangulated. And as somebody may be interacting with a game or with this image online, zooming in, zooming out, rotating it around, we can represent each of those transformations of a computer graphic with a matrix. And then we'll show that by composing a number of operations, that's going to be equivalent to looking at matrix multiplication. And we'll see how we can apply transformations to computer graphics. So rather than look at a really complicated composite thing of a whole bunch of triangles, we'll just focus on how any one triangle might be mapped around by these matrices. And just imagine that you can then apply these transformation matrices simultaneously to every single triangle that's creating the surface, say, for this horse in this example. So let's take a look on the next slide of a particular type of transformation that we can apply. Okay, so let's consider just one triangular piece of a larger image. And let's say somebody is zooming in on that image on a computer. So therefore, the transformation we would want to apply to that image would be a scaling transformation. So maybe somebody zooms in to 3 times magnify an image. So that would be a scaling by a factor of 3. And so recall that if we're applying this in R2, and the reason why I'm picking R2 is because computer graphics live in a plane, right? Our computer screen, so that we're dealing with images that are in R2. So I want to scale images by a factor of 3, then we can apply this matrix, 2 by 2 matrix, where the top row is 3, 0, and the bottom row is 0, 3, to any vector x in the plane. So for example, we've got this triangle, and it has 3 vertices. And let's look at where each of these vertices is going to get mapped under this transformation. So that first vector, or that first vertice that I've written over here at 1, 1, it gets mapped to 3, 3. So that vertex is going to wind up over here at 3, 3, right? So we're just kind of pushing 1, 1, so now that it's 3 units further away from the origin. Next, we could take a look at what happens to the vertex at 3, 1, and it similarly is going to get mapped 3 times further away to the vector at 9, 3. So that would be over here someplace. So this vector is getting moved 3 times further away, and similarly, we're going to take the vector, the vertex at 2, 3, and we are going to map that over to 6, 9. So here's 6 over 9 up. So now our resulting triangle would just be the lines that we use to connect these vertices. So that was going to take this triangle over here, and it's going to zoom it, it's going to expand it to make it 3 times as large. So that looks like something like this. So here we have a scaling operation, and you might want to think, well, what happens if I want to zoom in on this object, but I don't want to translate it? So we've actually translated this in the process as well. And so we'll work our way up to that process. Translations are not linear maps, so we're going to have to be a little bit careful about how we work translations into this process. But for now, let's just consider the linear map, which is given by the scaling transformation, which has this matrix. And we can see that this does have the effect of enlarging this triangle to make it 3 times as large. Okay, so now let's consider a different transformation that we've looked at previously, which would be a vertical shearing. So we can do a vertical shear to this triangle. I'll call this map V by taking each vector x in R2 and multiplying it on the left by this matrix where the top row is 1, 0. So we're not transforming anything horizontally. The second row is 0, 2. And so this last column that we get, 0, 2, means vertically we're going to expand things by a factor of 2. So we would call this a vertical shear by a factor of 2. And to see what this transformation is going to do to one individual triangle, we can apply it again to each of these endpoints and then connect the new resulting transformed vertices. So for example, if we apply this map to the point at 1, 1, it's going to get mapped to the point at 1, 2. So it doesn't change its x1 coordinate, but its x2 coordinate gets twice as large. And that's the same sort of transformation that we're going to apply to each of these points. So the point at 3, 1 over here in blue, that is still going to have an x1 coordinate that is equal to 3, but now the x2 coordinate, that gets mapped to twice as far. So it gets multiplied by 2, and now that becomes 2. So that point in blue goes from 3, 1 over to 3, 2. And then the last point that we need to map is the third vertex, which is at 2, 3, and it's going to wind up at 2, 6. So now we've got a new triangle that we can connect by joining these three vertices. So now we can see that this is a vertical shearing, meaning we've expanded the triangle vertically, but its width hasn't changed at all. So we haven't done anything in the x1 direction, but we're just stretching it in the x2 direction.